Great. Well, thank you for the very kind introduction. Today, I'm going to talk about power and sample size analyses that are required for multi-level and longitudinal studies. And the planned data analysis for these types of studies generally includes a mixed model to account for units of clustering. For example, patients clustered within hospitals, or to account for correlation between measurements collected on the same individual. So historically, it's been difficult to access easy-to-use software for these types of power analyses. Instead, the researcher has been required to generate complex simulations or simply implement a power analysis strategy that doesn't account for correlation. But today, I'm going to introduce the Glimpse platform that is free and easy to use and that can implement power analysis designs that account not only for clustering, but also longitudinal design. So please note, I will not demonstrate how to run a power analysis on the website today, but this presentation includes links to many resources that provide step-by-step instructions on how to implement different power analysis designs. So our group has no conflicts of interest to disclose. And then I'd like to introduce my co-authors, Deborah Glick and Keith Muller, who conceptualized, developed, and continue to upkeep the Glimpse website. And then I'd also like to acknowledge other members of the Glimpse team who've been integral for the development of the software, and who have also spent a lot of time developing educational resources for Glimpse. And also, I need to acknowledge that development of the Glimpse platform was funded through 5 NIH grants. And also, because of that, the software has been validated to industry standards. So today, I'm going to talk about the importance of power analysis, how to choose a power analysis design, the software, Glimpse, and 3 specific examples of study designs that can be implemented in Glimpse. And then I'm going to talk about how you should write up a power analysis, and then a few future directions for our group. So first, the importance. Power and sample size analysis is really an ethical issue. So as researchers, we seek to push forward knowledge and ideas in the scientific community so that others can continue on the quest by using and improving our ideas. But this only really works when the research is reproducible and replicable. So one very important component of reproducibility for studies involves sample size. So for example, if the sample size is too small, the study may be conclusive, while maybe a true difference between the groups may exist, the researcher may not have enough observations to see a statistically significant difference. And on the other hand, if the sample size is too large, then the researcher may use unnecessary or may cause unnecessary harm, or they may have results that are they're only statistically significant and they have no real clinical relevance. So power and sample size analysis is necessary for estimating the most appropriate sample size and for avoiding these issues. Simple, right? Well, that's only if the researcher has an understanding of how to implement the correct power analysis. So that's what we'll talk about next. So the first thing that must be considered when planning a power analysis is how well the plan design will align with the actual population characteristics, and also with the planned data analysis strategy. But let's take a step back. So in general, it's well understood that the conscientious study planner must align the data analysis plan with the actual study design. And prior to that, the study design must be aligned with the scientific goals. And this is the only way that the researcher may answer the research question at hand. But often, though, the researcher fails to align the power analysis and the sample size with the planned data analysis. For example, using a power analysis design that estimates a simple t-test to power a multivariable general linear model. This commonly occurs because there are no clear methods available for the appropriate power analysis. And in the case of power analysis designs for mixed models, until recently, we lacked solid statistical theory to generate a design. We lacked accurate computational forms to code the design. And most importantly, we lacked easy to use and validated software to implement the design. Fortunately, though, we now understand the theory and we do have accurate computational forms. And I know the majority of the people attending this webinar likely aren't biostatisticians, so I'm not going to present the theory and the mathematical equations. However, if you're interested, you can find everything in Muller et al. And Chi et al., whose publications are listed on this slide, and whose citations can be found at the end of this presentation. So often, when the theory and the computational forms are unknown, people turn to simulation. So a data set can be simulated using both sample size, the data distributions, the hypothesized mean differences and standard deviations. And while this may be reasonable for the highly experienced statistician and coder, there are a variety of issues that can arise with simulation. The first issue involves the amount of time that it requires to generate a good simulation. Simulations require a great deal of time to be written and debugged. And if the study design is modified, which happens all the time during the grant writing process, or a sensitivity analysis is desired, then the simulation strategy will have to be modified for each design change. And if the researcher wants to present something like the power curve shown on the right, then the simulation will have to generate enough points for the graphic. Lastly, it takes a tremendous amount of time to validate a simulated power analysis to industry standards. Without validation, how will the grant reviewers know if the program was written correctly? The second issue involves the single programmer. Simulations require programmers to make assumptions about the data. However, many studies are designed to collect and analyze data that's never been evaluated before. So it's very easy to make the wrong assumption. And then, as every programmer probably knows, it's really easy to make coding mistakes, particularly when you're under a tight deadline. So without extensive validation, those mistakes may never be found. Before I flip this slide, I want to take a minute to introduce the power curve shown on the right-hand side. This type of figure allows the person doing the sample size analysis to actually show how things may differ with the true values that come up when the study is being conducted. So this type of figure allows you to show how when the true mean difference is smaller or larger, the power may change, or how if the standard deviation that's true changes, how the power may change. So here in this graphic, you can see that we've actually plotted 3 lines, and each line is plotted by standard deviation. So in this case, we hypothesized that the standard deviation would be 3.02 nanograms per mil, which is the solid line in the middle. But we also show how the power curve would shift if the true standard deviation was smaller, 1.51 nanograms per mil, or larger, 6.04 nanograms per mil. Additionally, we have mean differences plotted along the x-axis, so the grant reviewer can see how power will change across differences in the true mean difference. So if there are extreme changes in the power across this graphic, then you may have to reconsider how your study is designed. Once you have the data for power curves, it's really easy to generate these figures, and they can save a tremendous amount of heartache through the research process. So now onto the software, which is probably the part most of you came here to learn about. As I've alluded to across this presentation, we have developed software steeped in mixed model theory that will compute power analyses that align with data analyses for multi-level, longitudinal, or even clustered designs. The Glimpse platform may be found at samplesizeshop.org. If you download these slides, these are hot links in each slide. The Glimpse platform, the homepage is shown here. So when you click on the link, you know you found the right place, and you know that because you found the large orange button that says calculate sample size now. Once you hit this button, the program will take you through the process of designing and running your own power analysis. The Glimpse platform is easy to use. The application is point and click, guiding the user through choosing the appropriate statistical test, type 1 error rate, and hypothesis test. The user is also prompted to enter units of clustering, repeated measurements, outcomes, predictors, group sizes, etc. And in addition to being user-friendly, development of the Glimpse platform like I said before, was funded through 5 NIH grants and validated to industry standards. So this means that the user can be confident in the results, and so can the grant reviewer. Even better, GLIMPS is free for everyone. So whether you're in academia, industry, or in between, GLIMPS is available for free. GLIMPS can be accessed through a web browser. You don't need to download anything on your computer, and all the computations are run on a remote GLIMPS server. This means that you can run a power analysis on the go using your smartphone, or you can run power analysis on your personal desktop while using the memory on your hard drive for something different. GLIMPS allows the user to download designs and re-upload them at a later time. So commonly this happens, but if you get stuck in the middle of a design, you can download it and then you can upload the file later and continue where you left off. When you finish a design, you can download the completed program. And if the study design is modified at some point, you can upload the program, incorporate the modifications, and quickly produce a revised result. And additionally, by saving the final program, you can ensure that your process is reproducible. So the GLIMPS software is widely used and has been cited by many NIH researchers, meaning that grant reviewers are often familiar with the GLIMPS platform and are generally confident about the resulting power computations. So now I'm going to talk about some of the actual designs that GLIMPS can use. So the GLIMPS platform was designed for a lot of different kind of study designs that relate to the mixed model. The first is a cluster or group randomized trial. So for example, participants might be assigned to a class, and then that class is randomized to either intervention or control. And the outcomes measured for the participants in the same class, they'll be correlated, possibly due to the person leading the class, or maybe because of the interactions between the classmates. Next is a randomized block design. So similar to the cluster randomized trial, participants might be assigned to a class. However, with a block design, participants within a class are randomized to either treatment or control. We can do multi-level observational designs. So multi-level means that there's more than one level of clustering. For example, you may have a study that's set up across multiple institutions where participants are then assigned to classes that are randomized to treatment or control. So in this type of design, you have participants clustered within classes, and you have classes that are clustered within institutions. So this means that you have to account for 2 levels of clusterings in your design. The next study here is an observational study with clustering. So here you may have an intervention that's implemented across multiple clinics, and the outcomes are measured for participants within the same clinic. The measurements that are measured for participants within the same clinic will be correlated. So this, like I sort of talked about before, may be due to, say, the doctors or nurses that are in the clinic, the location where the clinic sits itself, or maybe the demographics of the people that come into that clinic. Studies with clustering and repeated measures, we can do these as well. So an example here would be an observational study that's conducted across multiple sites, but that collects repeated measurements on participants. So here you could have sites that recruit women in early pregnancy, and then you could conduct dietary recalls across each trimester of pregnancy. So then you would have clustering within site and repeated measurements for each woman. And the last design I have listed here is a multivariate design. So a multivariate data analysis assesses multiple outcomes, traditionally ones that are measured in different units. And all of these are actually assessed in the same model. So this helps the researcher avoid issues with multiple testing, because a single hypothesis test can be used to assess if there were any differences across any of the outcomes. An example of this may be a researcher who collects measurements deemed to be the most important for cardiovascular health, for example, sleep, diet, and smoking status. And then the researcher can determine if any of those predictors of interest were associated, or any of those outcomes were associated with their predictor of interest. So The Glimpse team is dedicated to educating users on how to use the software, on how to implement different designs, and how power analysis itself, and how to do power analysis itself. A free short course is available on Coursera. If you download this presentation, the title here is linked to the Coursera webpage. And the course was designed for the scientist and includes information on different study designs, as well as step-by-step homework assignments. The material from this course is also on samplesizeshop.org, our webpage. And if you want even more to read, we have theory and applied articles linked to the course as well. So now I'm going to talk about 3 specific examples of study designs that you can implement. So these are all relatively, these are all relevant to actual diabetes and obesity research. The goal of this section is to introduce some of the study designs that can be powered using Glimpse. And again, I'm not going to show you how to implement these designs, but each example that I show you has a link to one of our guided modules that will show you how to implement that specific design. So the first study design is a single level clustering design. This means that participants are somehow clustered into units, which must be accounted for in the power analysis design. As an example, a single level clustering design was used for the National Diabetes Prevention Program FLEX study, which is a cluster randomized trial. And this trial proposes to enroll participants, assign those participants to classes, and then randomize those classes to either treatment or control. And here is a flow chart of the actual study design. And here is the unit of clustering. So this is where participants are in the same class that will likely have outcomes that are correlated. So participants in the same class may have correlated outcomes for many reasons. Again, there may be differences among the people teaching the classes. One of the teachers may be kinder or better at presenting the material, or there may be differences in how participants in each class interact with each other. So one class may have more extroverts and then more participation. The outcome of interest for this particular trial was the change in hemoglobin A1C. So the outcome was measured at baseline and again at 12 months after classes ended. And here's a visual of the hypothesized difference in hemoglobin A1C between treatment and control. By just looking at this picture, it appears that the power analysis should be very simple, for example, a t-test. However, the power and sample size computations would be incorrect if the user did not account for the correlation between outcomes measured from the same class. So it's a very important component of your power analysis. And then this slide provides a link, which is a detailed example of power analysis for a similar study about drinking reduction. And that's found in our module 1, or just click on the link and it'll take you right there. So the next example is a time by treatment interaction. So the example that I'm going to talk about here is the Community Activation for Prevention study, or the CAPS trial, which was a longitudinal randomized trial of gardening. So here is a flowchart of the CAPS trial. Measurements of fiber intake were collected at baseline, around 6 months during the harvesting season, and around 12 months during the winter that followed the gardening season. So this is the time component of the time by treatment. And further, since there were multiple measurements of time, we had to use a longitudinal study design that accounted for correlation within participants. And then in this study, participants were randomized to either gardening or control. So this is our treatment effect for the time by treatment. And then finally, here is what the hypothesized time by treatment interaction looked like. So we hypothesized that the trends in fiber consumption would be different across time for gardeners and controls, with the belief that gardeners would have higher consumption of fiber across time. And then once again, we have an example of a power analysis that's similar. which can be found on module 2 of our website. And this is a study about memory of pain across time. And then the last example I'm going to talk about is the subgroup analysis for a longitudinal study. So subgroup analyses assess the difference in an outcome by levels of the grouping variable. The grouping variable is often something that the researcher feels could be intervened upon to attenuate poor outcomes. So some examples of common subgroups that we assess are sex assigned at birth, region where a person lives, for example, rural areas versus urban areas, or differences in genotype, like mutation and wild type. So for our example, subgroups were considered in a study of the Healthy Start cohort. Healthy Start is a longitudinal observational study. Mothers were enrolled during pregnancy, and we're still following them now, and the offspring are about 8 years of age. We have data from both study visits that we've conducted with the children, but we also have data from medical record abstraction. So the proposed study wished to assess if BMI trajectories from age 2 to age 6 differed by sex. So in this case, we had a longitudinal component, which was the repeated measurements of BMI. And we also had a subgroup component because we wanted to see if those trajectories differed by sex assigned at birth. The goal here was to determine if neonatal adiposity was associated with the early childhood trajectories of BMI, and to see if that was modified by sex assigned at birth. So here's a figure of what this actually looked like. And you can see here that we have the longitudinal component of the BMI measurements across time. And we also have the subgroup component, which is biological sex assigned at birth. And you can see that the intercepts are different for the girls and the boys. And once again, we have the detailed example for a power analysis that's similar to this. It's a gene by environment interaction. It can be found on module 5. And just as a note for these examples, all of these examples provide screenshots for every single step that needs to be taken throughout the Glimpse platform. So they'll guide you very clearly through the process. So once you've actually conducted the power analysis, then the last piece is writing the power analysis so you can communicate your results to other people. Our group recently published a tutorial on designing, running, and writing power and sample size analyses for the longitudinal mixed model. This manuscript that I've shown here describes how to choose the correct power analysis design, how to select inputs for the power analysis, and how to write the power analysis methods and results. We have supplementary components for this manuscript, which include an actual Glimpse program that you can upload so that you can replicate the power analysis shown in the manuscript. And then again, we have step-by-step guided screenshots for Glimpse so the user can follow that as they run the program. This manuscript also provides a checklist for power analysis and a written sample of how the methods and results should be laid out in a grant. So it gives you a very nice example to follow as you write your own power analysis. But the most probably important parts of power analysis, the first step is actually describing your data analysis approach so you can get alignment between your data analysis and your power analysis. You need to figure out your type 1 error rates, which is generally 0.05, but sometimes if you have multiple testing, you might want to vary it and make it a little bit smaller, or sometimes with an interaction, make it a little bit bigger. You also need to provide all of the inputs for the power analysis so the reader can actually recreate your calculations and provide citations to justify all of those choices. This is a very sort of detailed process of figuring out what inputs to use, but this paper goes through finding inputs through literature searches or figuring them out in other ways. So it gives some really good ideas of how to do that. You also need to describe the effect of uncertainty. So for example, creating a power curve like I showed you earlier. And then you need to demonstrate feasibility of enrollment, plan for missing data, and then clearly describe power for a fixed sample size. So finally, future directions for our group. So currently, the Glimpse platform does not consider missing data. The software assumes that every participant has the same number of observations, whereas the mixed model can actually handle missing data. For example, in the CAPS gardening trial, we did not have all 3 repeated measurements of fiber for every participant. The mixed model accounts for this. However, Glimpse assumes that every participant does have all 3 repeated measurements of fiber. And in the case where there's no missing data, Glimpse is able to appropriately estimate the Wald F-test that's used by the mixed model by employing what we call the Hotelling-Lawley trace test. But when your power analysis has to account for missing data, we do have methods for adjusting the power and sample size output by Glimpse. And all of this information is available in a tutorial on the samplesizeshop.org website. And honestly, it requires just a simple mathematical adjustment that can be applied to the final numbers output from Glimpse. And while Glimpse can handle most cases pertinent to the general linear mixed model, there are still areas left to explore. Glimpse cannot handle an incomplete design where by design you've planned that there will be missing data across some of the observations. Glimpse also only allows continuous predictors as single covariates. It cannot handle unequal cluster sizes. It cannot handle things for the generalized linear mixed model, like binary, Poisson, or survival outcomes. It does not do anything with high dimensional problems, but no power software actually covers everything. So we still have a lot of room for future methodological research and to create extensions for this software. And the preferences of users is what we want to guide us. So if you use our platform and you have questions or you run into issues, we really want to hear, about it. We want to know what other things you'd like to see. And I have our Gmail account listed here on this slide, but this is also readily available on our website if you can't find the slide. So, and we are seeking funding to continue this project so we can continue to make it better. And here's a bibliography for this presentation. If you'd like to pull some of these papers, please access these slides from dkNET. Are there any questions?
Okay, now for the participant, you can unmute yourself or you can just ask question in the chat. We have plenty of time, can do the Q&A, or so you can ask a more detailed question, and you can start to try the tools and then see if you have any question. Yeah, so let me check the chat. Yeah, so there is a question from the chat. Let me check who is this. Okay. Yeah, so this one participant asked, do I need to join any community to use the software tool? Because it needs to be login, create account, and then is it free to take the module education course?
Yes, it is free to take the course. I'm sorry. Do you have the chat? Can I see it?
It's in the private, yeah.
Oh, in the private, okay.
Mm-hmm. So it's just ask about whether you need to join the community to use the software. Yeah.
No,
yeah.
Sorry. I was trying to stop my screen sharing. No, you do not have to join the community. It is free for all users. Am I echoing?
Yeah, I can hear, yeah.
Okay.
Yeah.
So you don't have to join our community or do anything like that. And all of our educational materials are also for free.
Yeah, and then there is one person asked where to get today's presentation. So I already sent the information and I will share this with them. Yeah. And then I think, okay. So are there any resource about how to select statistic tools? like I think probably they are in the links tour. So is that including in the module, or they need to have some take some statistics background like course before using everything? Yeah.
That's a really good question. Keith, do you want to answer this one?
Yes. So the short courses are designed to take someone as only introductory statistics class and move them to the point where they can use our software. So if you do have sophisticated multi-level modeling, then you'll understand what's going on much more easily. And if you don't, then if you find difficulty with the software, you can turn to the short course. And the short course teaches you both the material and gives you copious examples of the software itself.
Okay, thank you. So if I want to implement this to the lecture, how many hours can you tell about the module? Like to complete the module, how many hours a student need to take? Yeah. I think it's about the workshop that you mentioned, like 5 modules. Yeah. Mm-hmm.
Right. So the modules are available individually. You can do as little or as much as you want. When we taught it as a face-to-face course, it was a 3-day course. We've done it as a Coursera course, and that's we've given it for credit for typically 2 hours of credit at a university for the whole course. But again, it's flexible. You can look for a design consistent with what you've got, just look at that material and use that to use our example.
I have a question.
Yeah.
May I ask it?
Yes.
I have a question to Ms. Harrall. The question is, these days a lot of people do the multi-omic studies, and especially the longitudinal multi-omic studies. So where you recruit a group of individuals, and then you acquire multi-omic data, including transcriptomic, metabolomic data at 3 or more time points at different intervals, and at the same time you also collect the clinical data at different time points. Say, for example, if you are doing a dietary intervention or something, so you collected clinical data, for example, changes in HbA1c or BMI at different time interval, and also collecting the data for those multi-omic parameters. So is this GLEAM software can be used for that kind of power analysis, where like you have a lot of predictor variables, like all of these transcripts or the metabolites are too many predictor variables, but you have a smaller number of outcome variables like HbA1c or BMI.
Keith, have you set up a design like this where you have longitudinal predictors in your power analysis design?
Kylie,
Deb has raised
or
her
Deb,
hand
sorry.
and wishes to comment.
No worries at all. Dr. Doss, this is an excellent question. And it's very funny because we just wrote a grant to expand the Power and Simplify software to do exactly this and got it turned down. So all I can say is we're working on it. We are very aware of this need. We work in this area. We do high dimensional work. And we know that we need better in Power and Simplify software. So I have got your name and the other name of the other attendees here. And the minute we get it funded and finish working on it and put it up, I'll be sure to email you.
Yeah, thank you very much. I appreciate, I think, for this kind of multi-omic, multi-dimensional data, which is kind of new trend, and people struggle with the power analysis, especially where you don't know the effect size for each of these different quantitative variables.
I couldn't agree more. And to me, the real promise is that the real promise is linking to databases. For example, like the All of Us database or other databases which list epigenetics, like the EWAF Atlas or other things like that, so that people can not only ask questions like this, but also obtain input for their power analysis. And I wholeheartedly agree that this is something that we need to work on.
Thank you very much, ma'am.
There's one question from Krupa. Can you all send me the multi-omics data tutorials too?
Yes, Dr. Mysore, this is Deb Glick again. Sorry to interrupt, but the multi-omics data tutorials do not exist yet. We're still in the process of trying to get the multi-omics work, the power and sample size for multi-omics funded. So again, I've got your email. As soon as we get it published or funded, I will email you, but it's not up and out and available yet.
We do have papers published with the statistical methods. If you consult our citations, look for the Glick-Muller papers. Chi and Muller have papers on how to do data analysis in the high dimensional case and also power analysis. However, I'm warning you, those are statistical articles and we have not had the funding to reduce them to the practice of making it readily available for scientific practitioners and practicing statisticians.
Thank you.
So it's a great question. We're very excited about that. We're just not there yet.
Okay, thank you. There is also one question in the private chat. So I'm very new to this. Is there a way to validate my result after I use the software, or is there any help desk that I could contact if I have any question?
Yeah, this is Deb Glick again answering the question. And so the software is published with a validation study in it. You can refer to Kreidler, K-R-E-I-D-L-E-R et al. 2013 in the Journal of Statistical Software. This provides validation for the software and also references the published methodological papers that support the software. In terms of help desk, we have extensive online tutorials and training, including the course. If your power and sample size analysis is still failing, you can contact me personally at samplesizeshop@gmail.com. The email is on the website and in the software. I get emails from users all over the world, and we do try our best to help out. We can't help everybody. We don't have grant support right now, but I just do try my best. I think this is a public trust. We were paid for by 5 NIH grants, and we are used to write NIH grants, and so I really feel like this is something that needs to be supported, and I try to keep up on it. I can't promise, but I will try.